if I were to plot g of t, it will look something like this. It will look something like this. Great. And then it repeats itself only every 2 pi. Okay, the period is 2 pi. So the frequency actually gets lower or higher. It gets lower. Okay, so you would expect that the fundamental frequency of this thing should also get lower. Okay, so if you, one way is actually to do a direct substitution and say that I just need to make t equals to t over 2 in this exponential function. Okay, so when n equals to 1, the fundamental frequency is jt. When n is equal to 1, the fundamental frequency is j2t. So that this is actually lower in frequency by that. And this actually is the correct expansion, because I have stretched the time coordinate by a factor of 2. And this is the Fourier series expansion for the second one. Okay? And you can work on the compact form. Okay, I don't know if you want me to work on the compact form. It's pretty straightforward. Okay? The compact form is like the DC term, which is 2 over pi, like before. And then you have the rest of the term, which is written according to the textbook, is 1 over n squared minus 1/4 cosine of half the frequency. Okay, so this becomes n pi, nt. Okay, this is just nt plus pi. This is a compact form. Okay, just applying that formula that we have learned. So there are lots of exercises like this in the textbook. And if you have f of t such as this one over here, okay, what do you do? F of t looks something like this. E to the minus at for t less than t. And how do you find the Fourier coefficient of this one? Well, you can plot this function. It looks something like this. It goes to 0. Doesn't go quite to 0 yet at time t. And then it repeats itself. Okay, so this function looks like that. Okay, and then to find the coefficient of the Fourier coefficient, you just multiply e to the minus at, e to the minus j n omega naught t dt. And this is easy to integrate if you don't make mistakes. You combine them into exponential form and then integrate. Okay, I will not go into the detail, but you know how to integrate that. And then example 6.10. You have something that looks something like this. Theoretic function that looks something like this. Okay, this is 0t, 2t, and so on. And then when you multiply by the exponential form, you actually need to integrate only from 0 to t. And again, those integrations are straightforward and easy to do. I won't repeat them, unless you want me to repeat them. Okay. But let me look at example 6.14. Example 6.14 is kind of different from the other examples. It's not rote integration, but something else. is the Fourier series rule. Example 6.14 says this. If ft has Fourier coefficients that are given by capital F sub n, then the ft dt would have Fourier coefficients that are given by jn omega naught f sub n. And this is easy to show. Okay? F sub t is equal to f sub n e to the jn omega naught t, n equals minus infinity to infinity. If I differentiate this equation once, I will bring this jn omega naught down when I differentiate this function. Okay? And then I have this n omega naught t. So this is my new Fourier coefficient, fn prime. And that is just the rule. It's very easy to prove. Okay? And the rest are, I think kind of mundane. There are many examples. There are altogether 14 examples in this section. I don't think I can go through all 14 of them. Unless you have popular demand, you'd like me to go through one of them in detail, but it's actually a lot of rote algebra. Nothing more complicated than integrating exponential forms. Okay, you don't even have to use the integration by parts rule that I alluded to in any of these examples. Just have to keep things very correct. But there's a phenomenon called the Gibbs phenomenon that I like to describe. So this is the periodic function, and in principle, you can write this as a sum of Fourier coefficients. Okay, that is in principle, this is true. Mr. Fourier was correct. You can add this series up and get the right hand side to be equal to the left hand side, but in practice, that doesn't work out to be quite true. If you add terms, say if you add a finite number of terms, you don't replicate this function exactly. You replicate a function that looks something like this. Okay? And you get an undershoot and overshoot at this junction. And similarly, if you would add up the Fourier series, if you have a finite number of terms, you have something that looks like this, and then maybe an undershoot and an overshoot, an undershoot. Okay, an undershoot and overshoot and so on. This kind of overshoot and undershooting is called Gibbs phenomenon. Okay, it's called Gibbs phenomenon because the Fourier series does not converge well. It does not converge well. It converges very slowly. You have to add many terms before it converges to the right value. But even if you add many terms, it converges not quite to the right value, and it's always slightly off. Okay? Yes? Yu Chun Chang? You don't have a question? Okay. So, this kind of slow convergence is known as Gibbs phenomenon. Intuitively, you can understand it this way. You can understand that when you do a Fourier series expansion, you're trying to represent the function with sums of Fourier modes. And all these Fourier modes have different frequencies. Okay? Some of them have low frequencies. You get exceedingly higher and higher frequencies. And finally, in good terms, it's very high frequencies. That is the principle of Fourier series expansion. And Fourier says that you can add these Fourier modes up to get any functions that you want. But say if you have a function that has the jump discontinuity like this, you will need very high frequency Fourier modes to reconstitute this part of the function. That means that in order to reconstruct this part of the function, you need Fourier modes that are extremely high frequencies. Okay? Otherwise, there's no way you can emulate this sharp jump. So you need exceedingly high frequency components to reconstitute this jump, this continuity, and the convergence is very slow. Okay, you need many of these Fourier modes, and they try to add up with each other to try to emulate this continuity, but not always quite there. You're not always quite there. And this phenomenon is called the Gibbs phenomenon. And in order to avoid this Gibbs phenomenon, one way is to not try to be so ambitious and use Fourier series expansion to expand this function. Be less ambitious and use it to expand a function that is slightly smooth. This function on the right-hand side is smoother than the function on the left-hand side. So if it's smoother, you will not have the requirement for a lot of high-frequency components in order to reconstitute this function. And you will not need all those Fourier modes that are very high in frequency in order to reconstitute this function. And if you do a Fourier series expansion of this, you find that the convergence is very good, okay, very quick. I like that one over there, okay? The existence of Gibbs phenomenon disappears. This is just an intuitive way to explain it, okay? Intuitive way to explain it is because when you have a jump discontinuity, it has to be constituted by many Fourier modes of very high frequency contact, very oscillatory functions, and they have to be added up together to try to emulate this jump discontinuity, and it's very difficult to do. Okay. Are there any questions regarding Fourier series expansion? If not, then I'll let you go. Okay, have fun, and you have exam next.